thank you very much for the invitation. I feel like if Hunter felt a bit out of place, I don't know where am I, but anyway. So I'm Ximena Schmidt. As I said, I'm a senior lecturer at the Chemical Engineering Department in Brunel University, and I mainly work on sustainability assessments of food systems. So although I'm not specifically working only in fertilizers, and valorization of waste is one of the areas if we consider the food system as such, right? So about the talk today, I thought, what about giving a little bit of a life cycle perspective of fertilizers used from valorized resources? This is more or less what we are going to talk about it. And this is a bit about me for those that I haven't talked about it. I'm from Santiago, the capital of Chile, where I did my degree in engineering, and I moved to Manchester in 2011 to do my PhD there in the sustainability group at the Chemical Engineering Department, and stayed doing my postdoc there. And in 2019, I moved to Brunel University to do, I was a global challenges researcher, which was a great opportunity, but COVID came. So it was like, oh God, I can do so many things, and really I couldn't do much. But anyway, then I joined the chemical engineer department, and this is Brunel University. It's not a Russell Group university, however, it's part of the University of London, which is 18 universities really, like we are all together under this umbrella. And it's a university in the West London, very close to Heathrow. For good or for bad, I don't know. People really like that sort of stuff. And it's quite unique in a sense that it's very local. So we recruit a lot of the local students in the West. Our community is very diverse with a high population of Black and Asian communities. So it's very interesting and very rich in culture and diversity. And this is the chemical engineering department. It's a very young department. We started around, I think, 2018 to start doing our program, but now we have run it for around 5 years. We are accredited by the ICME, and we are a bit more established. So yeah, very small amount of stuff. So in terms of motivations, I think climate change is one of the main drivers of my work and life in a way. And in particular, because if we think about the food systems, 30% of the greenhouse gas emissions globally are coming from the food system. So although we have been focusing a lot of energy, which is a bigger chunk, then the harder part is going to come from the food system. So when we have everything based on renewable and decarbonized, this is going to be the harder part, in particular because, as somebody mentioned yesterday, behavioral change will be big. What we eat, how we eat it, where it's coming from, how we grow things, where we grow them, etc. is going to be big. And I think fertilizer is one of, well, feedstock, animals and fertilizers are one of the big issues when we talk about the greenhouse gas emissions. And I think that also connects with what we talk about when we talk about why circular economy is such a thing. Is because the linear economy was one of the main causes of, including if we talk about industrial revolution and so on and so far, where we are today, where we have a resource scarcity, we have a population growth that we cannot really match up, and climate change. So all these big three pressures, as well as others that we can interconnect and debate which one is first and which one is direct or indirect. So this one is kind of the idea that we think probably we could do something about it, right? So if we think about the core elements of circular economy, it's about eliminating waste and pollution. So probably the concept of eliminated waste will be more about, let's call it resources instead of throwing away, right? This is what we are probably looking here. Also looking about how we circulate products and materials, so how we make them to stay for longer, maybe be transformed, maybe be maintained, and so on and so forth. And of course, about regenerative nature. So how we combine that? Perhaps we have been focusing in certain areas. Some people are looking at more specific aspect of these three elements, but I think we do need to think in a more systemic view. So we cannot just pick one and get rid of the other one. So I think that is what we try to encourage ourselves, I guess. And a lot of policies have been created and more have been. So that one was in the UK, we have one has been taken away, and then we have another one, depending on the government, but these are kind of the big ones. And I want to highlight the one that connects with the fertilizers, that talks about this connection with circular economy, using biowaste and so on. But the problem with these regulations is they are not standardized, they are kind of goodwill, they're kind of encouraging, but not necessarily, they open this ground and motivate you, but we are all like running with our own ideas in a way. And we saw in some of the talk, like the organic accreditation or certification actually not necessarily match with what has been sort of motivated or pushed for, right? And this motivation, if we talk about what I do, all the stuff about how we understand the environmental impacts of different systems is one of the big angles that is coming from the circular economy action plan or any other circular economy policy, but also connected, or not but together with all the sort of net zero. So we are kind of moving around a circular economy, net zero, not necessarily they really fit, right? And that is how perhaps circular economy, life cycle assessment has come like in a big push. So this is not a new tool. It's a tool that has been created, I think it's like in the 80s, started very big, 80s and 90s, and then sort of dry out and then was pushed back in the last 20 years. And when we talk about life cycle assessment, it's basically to try to integrate and see this sort of systemic view of products, systems, and services in a way that is not just about what I make or what I use, but also try to understand how we can see the whole life cycle, or people could call it like the supply chain, and so on and so forth. So I'm just going to give a little basis of this, and it is a standardized method. So it's the 14040 and 44. Here is not rocket science. If we all have done projects, so more or less, we have an objective, we build the data, we carry out certain assessment, and we have results, right? So this is more or less the 4 steps of the methodology. And of course, we have iterations, so as we have done in different projects. And the idea is to try to be comprehensive and transparent as any other ISO standard. If you have worked with them, it's kind of a guideline of how to carry out and how to have this sort of consistency and transparency. And it's part of the management system standards too. So this is kind of the core. And when we try to see about life cycle assessment is perhaps as consumer, we look about the end use or how we use the product, but we also need to understand what are the other stages and who are the other stakeholders involved on that. And that's why we try to model through this analysis. So if we think about how we unpack this, again, perhaps for all of you, it makes a lot of sense in terms of the different steps, but perhaps we can see that there are certain aspects that are quite important, and that they need to be consistent. So if we know what is the purpose of this study, we need to look at what we call functional unit or a reference flow. So that needs to be connected with what we want to study, and then how we build our inventories, or what are the data that we are using, if there are surveys, if there are models, if there are interviews, and so on and so forth. What sort of methods are we going to use in terms of the impact assessment methods, and how we show the results. This is more or less how we unpack it. And sounds like a lecturing about this, but it's important because when I came before coming, I was like, I'm just going to look at all the results about organic fertilizer or bio-based fertilizer. So we are going to have a range, and we are going to know all the impacts. Well, actually, the literature shows that it's very difficult. And it's very difficult because we have challenges in how we apply that methodology. And as has been said before, what are the sort of standards of what is the consensus about how we treat these fertilizers in relation to the modeling aspect. So some of the challenges that I found, that are common in terms of this kind of analysis is the consensus. So when we talk about, for example, energy system, there is a bit of more a consensus because it's been studied for longer. If we talk about carbon capture, there are some technologies that they have faced the problem of everybody's doing whatever they want or what they think is the best, but a policymaker cannot really make sense of this data because if they don't know, they're just going to pick numbers. However, those numbers are not necessarily representative or comparable between each other. So when I look in the literature, I, of course, found somebody that wanted to do something like this before, reference 6 at the end. So, and they said, like, yes, there is, again, a lack of consensus of the methodological choices to understand what is the actual impacts of the bio-based fertilizers. And these are kind of the challenges that are being highlighted. And I want to say that these are really common around any sort of life cycle assessment. So what is the goal of the study? So why are we doing this study? What is the scope? So what are we integrated? Are we doing, for example, farm gate? Are we doing the whole life cycle? Are we doing it at consumer? So that is common. The same, the functional unit, so we can save per kilogram of product or per kilogram of application or the kilogram of or megawatt of energy produced or heat. So that is very, very common. But then when we talk about the bio-based fertilizer, there is this extra aspect. And I put emission models, by the way, in between, because if we are looking at any sort of food product, when we look about how we are modeling the emissions from fertilizer application, from pesticide application, then we found a lot of differences. So we see that depending on the model that people use, they could have a different value at the end of the day. But then in particular, when we talk about bio-based product, we see these two extra challenges. So the last one is connected to if it's waste, is zero burden, so it comes free of anything, or actually this waste is coming from another product, from a system that is actually, yes, is emitting impact. So if I have a system that produces, for example, rice, we have rice, the grain that we are looking at, but also we have straw and maybe other sort of residues. Those residues are actually with an impact from the production of rice, right? But this is something that is still really contentious. So people keep putting, and I am one of the ones to blame as well, putting that, oh yeah, it's waste, so zero burden. So we start with a fresh, nothing, zero, very clean product to then produce whatever we want to do. And that is big. It could be very big, it could be very small, but influence the results. And the other very important aspect is the biogenic carbon management. So like there are a lot of models and there are a lot of information that probably some of you have actually seen, like what is the carbon content? Is the biogenic carbon, is the carbon content going up? It is actually increasing the carbon. So a lot of those models, some people have included, actually, if you use this fertilizer, you are actually increasing this soil amendment. Therefore, you have X, Y, and Z aspect that will influence the model. Similarly, are what we call credits. If the system actually is having biogenic carbon, so we are avoiding to use anthropogenic carbon or fuel, fossil fuel one, then we have these credits. So then is when we are getting in this, but it's net zero, or this is what people want to see. I want to have this product that is actually net zero, or what we call net positive. And then it's all this new door of, can we trade some carbon? Can we do? So this is what is quite interesting because everybody wants to have this net positive product, or actually at the end of the day, can we sell carbon? Can we trade them? So all these sort of aspects are quite interesting because then when we go to the literature, we can find products that are minus whatever, so it's like great, or others that are actually still lower than the mineral fertilizers. But if the mineral fertilizer production system actually is also getting some credit from creation, for example, we talk about energy or whatever, or using energy sources, then the competition is not going to be that different. So this modeling aspect is very important. And are you going to have the time to go and read everything? And so you're just looking for a specific value or a range of value to show, to see what is your product. So with that in mind, I was just going to go through some studies that again, that I can highlight what were these challenges in these sort of studies. So here we look at the environmental impacts of valorizing spent coffee ground. Somebody here used it. And we basically what we did, this was the goal of our study. So if we see, we did look at, for example, composting and direct application, digested, but our main goal was to see what can we do with spent coffee ground. So if you have a lot of spent coffee ground, what will be the best alternative for valorizing this residue? And we look at all this, with all this sort of option. So if we see the third challenge is the goal is completely different. Although we are producing fertilizer at some point or some soil enhancement, it's very difficult to understand. So what is the impact of this? If actually my system is looking at what do I do with spent coffee ground? So it's very difficult to translate this result to maybe you are looking, oh, what happened if I make fertilizer from spent coffee ground or biochar or whatever, right? So there are studies doing this, but not necessarily are easy to extract this information. Similarly, for example, again, as I said, we use a ton of spent coffee ground, but actually this could have been, you know, the area of application, or it could be the specific mass of the crop. It could be the amount of nitrogen content, the phosphorus content. Like there could have been many other functional units to analyze. So again, how do I translate this to something that is meaningful for example, bio-based fertilizer? And again, this is the system that we use. So we can see that some of the challenges will be the scope. So we have here all the spent coffee ground, and we included only the different treatments. And yes, we did include the transport. So another study could have been since the production of coffee, right? Or using the coffee in a coffee shop. So then how do, yeah, I mean, I could tell you how to do it, but not necessarily it's easy, right? It's going to be complicated. And then we did include the infrastructure, but not for other things. So again, you have things that have been picked out for reasons. Hopefully they will say why, but it's not really that easy to just unpack. Similarly, we have what we call allocation methods. So for example, here we did system expansion. So in that case, we are adding the credits of avoiding the use. For example, here we produce glycerin in the biodiesel production. So we are adding these credits of the avoiding of using glycerin from fossil fuel processes. Here we are avoiding, you know, the electricity production and so on and so forth. So these credits, although it's a good practice, if you have a very dirty electricity mix, it's gonna make this system to reduce your impact massively. So you could get to net zero production system, but in a very specific point of life, right? Like when your electricity mix was really heavily, for example, coal-based. But in 3 years, probably you have already a very big policy of solar power or whatever it is. So these values are not necessarily gonna be really reflecting of the reality of the system, right? And then we have what we said about biogenic carbon and feedstock. So for example, this one we said, spent coffee ground, zero waste, great. But actually we should have included all the impacts, or at least show the difference. So that happens depending on what is the reason of this study, right? And this is how the results look like. So yeah, so for example, biodiesel is very good. You know, we have a specific results that if you are actually looking, hey, what about the fertilizer use here? You know, you will have to do a lot of calculation and maybe you won't be able to do it anyway. Here is another example where we look at the modeling aspect of fertilizer and pesticide use in barley, in Italy and Denmark. And again, so for example, here we are not looking at the amount of fertilizer used. We are looking at the amount of grain, or in this case, barley produced as a functional unit. So all the results for you to then look at, oh, what about the fertilizer? You have to really go back and do all the calculations. So for example, using different models could change the results, like for climate change, around 15% difference. But if you look at eutrophication, it's around 89%. And the difference of these models is like how much information you have to actually be able to use a simplified model to a much more robust, where you have to put, you know, temperature, like if there is a wind when it was applied. So yeah, if you work with with farmers and so on, maybe they could tell, maybe they don't, and you will have to go and look for that information. But maybe person like me that probably are going to gather information, maybe I'm going to have to look for the simplified version first. And so there is a lot of the range of these values need to really account for the differences of them and how these results were developed. So if we see in this study, we have all these sort of challenges present. We didn't look at this because of the type of, we were using waste really. So it's quite interesting to understand that these results really need to be looked into, like don't just buy one result, whatever you find, like really try to look at it. And have a little bit of more time. And then I also wanted to look at one study that it's not LCA study of this, but we look in Chile, like what will be the aspect of the resource, what are the resources that could be valorized in Chile? And what we did was basically looking, in this case, we looked just at bioenergy because it's quite a much more simplified version. So we were testing what are the databases available. So what we try to look is what are the residues generated in the country. And we look at also at every region. So to say, can we see if we can match the energy demand, in this case we were looking at energy, with the resources that are available and the potential to use it as bioenergy resource. So this is more or less the distribution. So this, I'm going to use more than so the regions where we grow more food and you also have livestock are the ones, of course, with the higher resources available and therefore the bioenergy potential. So here's the country, is very long. Here we have regions divided. So this part, the bottom part, the Patagonia, is very similar like the north of Scotland. So you see a lot of sheep, but not many vegetables or crops or anything. While the central south regions are here are the ones that has most of the growing capacity and where it's more exploded. And here we have the energy demand, which is quite interesting because here the second region is where the Atacama Desert is. So if you see, we have very little like bio-based resources, but we have a very high demand, and the high demand is because of copper. So all the mining production here, like the biggest mining areas in the country are in these two regions. So the energy demand is very high, but bioenergy clearly is not going to provide that. So solar panels are put there for good or for bad. But then we have, of course, the central region where we have the metropolitan region, which is Santiago and so on. So it's kind of interesting that some areas can be actually overlap with bioenergy resources. And here we divided by the specific, annual crop, horticulture. We also look at municipal solid waste and the livestock. So in a way, it's quite interesting to see that there is some capacity. And the next steps will be to see, can we look at what are the nutrient demand? And is this some potential here with this data that we have? Who knows? So these are sort of some of the final remarks. I think I'm kind of on the time. So as our colleague here, Hunter, said, lack of standardization is a massive deal here. And I think it will be very important if we want to see, is there any support, any sort of credit that we are thinking in terms of economic support or, policies that will be enabled. They will have to account for this sort of aspect if there is any sort of carbon tax, for example, or eco-labeling, because at the moment, people are running with their own thoughts. And there will be a lot of conflict of interest in all these studies. So, thank you so much for this invitation.